Yes, I would like to talk a little bit about this topic. Maybe a disclaimer, there's going to be almost no quantum, a lot of topology, but very little quantum. And it's going to be very basic, very elementary. It's going to be only one talk. You will see the proof, the story, everything. But very elementary. I hope you will enjoy it. So maybe I give you just a short plan of the talk. So first, I will just give a lengthy introduction to the subject, where results of a couple of people that are present in the room will be mentioned. Then the second, I will introduce the main tools we will use here. In the third part, I will give my results, our results, because it's joint work with Anthony Conway and Cleopatra Zakharova. And Anthony Conway has got nothing to do with John Conway, unfortunately, but he's a very, very bright grad student. Okay. So the introduction. So what I want to look at is, I'm going to kneel, I think, most of the talk. So this is a mu component link. Okay. In S3. And you see immediately that by using only crossing changes between different components, you can turn this link, any link, into the split union of its components, right? You just tear them apart, okay? So the question we ask is, what is the smallest such number? And this is called the splitting number, okay? So this is the definition. So splitting number, so the splitting number of L, that we denote by SP of L, is the smallest number of crossing changes between different components of L to turn L into the split union of its components. I don't know if you can see when I write all the way down there, but okay. Okay, this is clear, right? So maybe I'm just going to start with a very basic example. So let's consider the Whitehead link. Okay, it's the Whitehead link. So here, what I will do is simply I will make a crossing change here and there. And you see that then you have one component that is completely on top of the other. And so this leads to the split union of its trivial components. And so by this, we see that the splitting number of the Whitehead link is less or equal to 2, right? When you have a diagram and you have an explicit sequence of crossing changes, it gives you an upper bound on the splitting number. And I took this example for a good reason, because one could have chosen, well, actually it's not allowed, but you see that if you actually change this one here, then what do you get? And this is an unlink. But this is not allowed, okay? So here this example was chosen just to show you here, I don't do the splitting number of the Whitehead link is, in this sense, is not 1, it's at most 2, okay? So this is not allowed. And so the question is, how can you determine this splitting number? Okay, it's a very natural integer to associate to a link. For if you're interested in knots, then there is nothing, no theory, right? But if you're interested in link, okay. So question. So how to compute the splitting number? So in this introduction, I want to give you several results that are known. Okay? So the first result I want to talk about is completely obvious. Well, okay, so the first one is really obvious. It's that the splitting number has the same parity as the total linking number. I think this is quite clear. And so this implies in particular that for the Whitehead link, so let's say that this is Whitehead link. So for the Whitehead link, it's 0 or 2. Then there is a lower bound that is totally elementary, and that I will give you now. Okay. Whenever you have two components, let's set B linking to be equal to 0 if this sublink is split, to be equal to 2 if the linking number of these two is 0, but it is not split, and to the absolute value of the linking number of these two, else. Then it's very easy, it's actually very easy to see that the splitting number of a link is always greater or equal to this. I think that's quite clear. So this we will call the linking number bound, or let's say the linking bound. Okay. So that's the kind of totally obvious things. Can we say more? So the first people to say more about this were Batson and Seed. That was in 2013. And their paper got published in Duke maybe 2 years after that. So I said there would be no quantum in my talk. It's not completely true. So here, actually, they used Kovanov homology. So used Kovanov homology. Basically, what they did is they found a new spectral sequence that started at Kovanov homology of the link and converges to the Kovanov homology of the disjoint union, the split union, and the page where it collapses, it gives a new lower bound on the splitting number. So to obtain a new lower bound. So that's very exciting. So one of them, I don't remember which one, is very good at computing, so he programmed something, and so they computed for every prime link, this new bound for every prime link up to 12 crossings. So there are like 5,200 and something links, and they compared their new bound to the original linking bound. See, okay, can Kovanov homology do much better than the totally obvious thing? And the bad news was that out of these 5,200 and something links, only 17 gave, in 17 cases, were their bound better. But okay, so here they obtained, so it's better than the linking number bound for 17 links with less or equal to 12 crossings. And for these out of these 17 links, there are 7 where they were able to determine the splitting number. So for 7, the splitting number was then determined to be 3. And for the 10 remaining ones, they could not say. For the 10 others, the splitting number was 3 or 5. I think I will use this chalk, it's a bit better. And then comes in the same year, Cha, Friedel, who is sitting right here, and Mark Powell. So they introduced 2 new methods. So I will not say too much about these methods, but I will name them and tell you a little bit what they're good for. So the first one is called, well, it's based on covering link calculus. And so I don't know if you know a little bit about this technique, but basically the idea is to take one of the components of the link and then to consider a branch cover, maybe a twice branch cover over this component, and you find yourself, and then you look at the inverse image of the rest of the link in the new manifold. And basically what they did is so I'm absolutely not going to be precise, but basically they said that if the splitting number here is less or equal to, let's say, some alpha, then this other link that I will call L tilde, that is in another manifold in general, well, let's say here in S3, L tilde will bound a smooth surface F embedded in B4 with the Euler characteristic of F given by alpha. So it's not equal to alpha, of course, it's a complicated thing, but. So what they do is they transform this elementary problem of computing this splitting number into a very difficult problem, but sometimes you can solve it. When does a given link bound a surface of a certain genus in B4? So you probably know that that's one of the most difficult problems in knot theory, but nevertheless, there are some methods, so why not try? Okay. The second technique they used was Alexander polynomial. Namely, if the multivariable Alexander polynomial of the link is not 0, then the splitting number is greater or equal to mu minus 1. Furthermore, if the splitting number is equal to mu minus 1, then the multivariable Alexander polynomial is of a very specific form. So it is namely, so I will again not state the whole thing, but basically it's of the form, the product of the individual Alexander polynomials of each of the components times a norm, basically, times p times p bar and some other factors. But anyway. So they were extremely, I mean, these methods are very nice and they were extremely successful in applying them. Namely, they were able, using these methods, and of course the linking bounds, so this enabled them to do what? First, to compute the splitting number for the 130 prime links up to 9 crossings. Okay, it's nice. and for the 17 Batson seed links. And for the 17 links of Batson and seed. So that's very nice, and of course, unfortunately, in this very particular case, the Kovanov homology does not seem to be very powerful compared to very standard techniques. What can be said about these things? So first, so maybe let's say A and B. So this is all very nice, but I guess Stefan will agree that, as I said already, here you transform a very elementary problem into one of the most difficult problems in knot theory or link theory. It's in general extremely difficult to tell whether a given link bounds a surface of a given Euler characteristic in B4. Of course, there are many things that are, many techniques are known, but very often they end up making one specific argument for each case, because each time you have your new link and new bound, and maybe sometimes you can use the signature to show it doesn't work, sometimes you can use the S invariant, some more quantum topology coming here. Sometimes you use the twisted Alexander polynomial, you have all these, but in some cases it's a full section of the paper just to treat one link. Okay. So, okay, and then for this case, it's a very powerful tool, but of course it only allows you to show that the splitting number is strictly greater than mu-1. If you have a one component link and you want to show the splitting number is actually 5, this is absolutely useless. Okay. So these are very nice tools, but they're kind of specific, and it's not like a uniform lower bound that you would use all the time. Okay. And then there is one last paper I want to quote. So it is of Borodzik and Gorski, who's also sitting here in the room. So this was very recent, in January, I think. They posted a preprint on the archive. Again, I will not be precise, but they use Hegardt-Fleur homology. So use Hegardt-Fleur homology to give lower bounds, a lower bound, okay. To give a lower bound on the splitting number. And I will give you in particular one example that they obtain, which is nice. So in particular, what do they obtain? You fix a positive integer and let L be the two-bridge link with Conway normal form C2A, 1, 2A. And I'm just going to give you an example so you see what it looks like. So I just have to see which one goes on top. I always get confused. So for example, this is the case A equals 4. And I guess you can guess a little bit the general form of this thing. So you have 4 crossings, 1, 4. And you see it's quite clear from this diagram, so it's a 2-component link, right? And it's quite clear that the splitting number should be at most A, right? Because here you just pass it through. Yeah, you're right, yeah. Sorry. Thank you. Thank you. And so here you see that, so their results, they show that the splitting number, so here in this case, what would it be? So A equals 2, and here you would need 1, 2, 3, 4, right? 4 crossing changes, so it's equal to 2A. Again, the lower, I mean, the upper bound is completely clear from this drawing, but you might think, okay, maybe there is a smarter way to draw it, and then they show this. Okay, that was the introduction. Any questions so far? Okay. So what I want to show you today is a new, completely general lower bound on the splitting number that is very elementary, very easy to compute, and quite efficient. Okay. It is not strictly better than any of the methods that I said today, not of a single one. But if you want to compute splitting number, you'd better start with this one. That's what I claim. Okay. So that was the end of the introduction. I'm gonna now talk about, we're gonna forget about splitting numbers for a while, and I'm just gonna introduce these so-called multivariable signatures, and then in the last part, I'm gonna show you how to use them. So, signatures. You probably all know about the Levin-Tristram signature of a knot or of a link. And what I want to explain to you today is a generalization, a multivariable generalization of this signature. So, okay, so what I need to define is a so-called C complex. So that's the basic geometric object here. So a C complex for an oriented link in the sphere is a union, let's say S, of oriented surfaces such that, so there are three conditions. And again, you should think, if you think in terms of one variable or in terms of a knot, this will simply be a ciphered surface. But, so this is the generalization of the ciphered surface. So, first condition, for each I, Si, well, the oriented boundary of Si is equal to Li, and let's say Si is connected. So what I'm saying here is you have a bunch of connected ciphered surfaces for each component of the link. Okay? Now, of course, what happens is that these ciphered surfaces, they will intersect. Okay? So what you want to prescribe is the way they intersect. That's the second part. And the third one, maybe I will start with, the triple intersections are empty. So no triple intersections. And what about the pairwise intersections? Well, so is either empty or a disjoint union of so-called clasps. And I'm going to draw a clasp intersection for you. You can guess a little bit how it looks. So if one surface comes like this, this is a clasp intersection. Okay? right? So the first fact is every link admits C complex. Any L admits A, and you can assume it's connected actually. C complex. Okay, so remember we were talking about ciphered surfaces for not so. Of course, this I'm not going to write it down, but of course, in the case mu equals 1, you just have a ciphered surface. That's it. Okay. Now, what are ciphered surfaces good for? Basically, the idea now is whatever you can do in one variable for links or knots using a ciphered surface, you can do in multivariable using these C complexes. The one thing we're going to focus on is, again, the signatures. How do you define signatures? In one variable, you use the ciphered form. Okay, now, how do you, so what is a ciphered form? Ciphered form, you pick a direction of your surface, and you push a cycle off this surface, and you look at the linking number of the cycle pushed off the surface with another cycle. And here you see we have a little problem, is that here you don't have only one or let's say two ways to push your cycle off, but you can choose two different directions for each surface, okay, for each component. So what you need to do is to fix first a sign for each component. So what we're going to do now is fix epsilon, which will be mu signs, and consider, I'm going to write it by alpha epsilon. It's a bilinear form on the homology of the C complex. And whenever I have a cycle X, cycle Y, I associate this, the linking number of I epsilon X, Y, where I epsilon X denotes the one cycle X that is pushed off the epsilon I normal direction of Si for each I. Okay? With I epsilon X pushed off the epsilon I normal direction of Si for any I. Okay, so now we fix bases of the homology, and we write A epsilon for a matrix. So fix the bases and write A epsilon for the matrix epsilon. Yes?
When you write each one of S, you mean really S as a subset of the sphere or the abstract geometry?
So S as a topological space, and it's not a disjoint union. So here maybe right?
Really S even sphere.
Yes. So it means you have, yes, so you understand the answer, but so you will have the homology of each of the components plus big cycles that are going through the different components. Yes. Okay, a couple of remarks. The first remark is that, so there are 2 to the power mu different matrices, but actually they're related in the same way that for a usual ciphered matrix, if you push in one direction or the other, the two matrices you get are related because one is a transpose of the other, right? For exactly the same reason, we have that for any epsilon, A minus epsilon is equal to A epsilon transposed. So really you have 2 to the power mu minus 1 different ones. And the other remark is if mu is equal to 1, then let's say A plus is a ciphered matrix in A minus is its transpose. Okay, so let's see how I'm doing. So maybe I'm going to just give you a very short example, just to show you that these things are very elementary to compute. So I'm going to take again this Whitehead link I had started with. Okay, that's the Whitehead link. And what I'm going to do, I'm going to deform it. So here, I'm going to pass around like this. Okay? And now I wonder if you can already see a natural C complex for this. So for this component, I just take a disk that I twist. Okay? And here I have another disk, and they do intersect in two clasps, right? So here maybe I'm just going to change a little bit drawing here. Right? You see it? And so this is the example for an example for the Whitehead link. And I'm not going to compute everything, but you see that this thing here, S, so that was an example, you see that it has the homotopy type of a circle, right? So H1 of S is Z generated by some cycle X that I'm not going to draw here because it's going to make the triangle a bit too heavy, but it's a cycle that goes here around. And I should have drawn orientations, but actually one can show it's not difficult that A epsilon is equal to -1 for any epsilon in this case. And again, so maybe let me just draw the cycle once. Okay. And now when you push this X, again, you have 4 ways to push it off. So you see, and you will push it off in 4 different directions, 4 different ways. It's going to link itself. And you just compute this linking number, and you see that you always get -1. This was just to show you that these things are just very easy to compute. So once you have these so-called generalized ciphered forms and matrices, you can do a lot. You can play around a lot. You can, for example, construct the Conway potential function in this way, or several other things. But again, what we're interested in now are the signatures. So what do you do? So set. So you fix some element. So you fix mu elements of the circle that are different from 1. This I will denote by T mu, maybe a star. And consider and set. So I will write a big expression that's going to be, so I make a sum over all these signs, all these epsilons, to the power mu of one of them, product 1 minus, omega I bar epsilon I times A epsilon. This is some combinations of these different ciphered matrices. And you notice that since, by this remark here, since A minus epsilon is A epsilon transpose, this matrix is actually Hermitian. So this is Hermitian. You have a Hermitian matrix, so you can consider its signature, its nullity also, the number of zero eigenvalues. Therefore, we define the multivariable signature and nullity of L are the functions sigma L theta L defined on this mu-dimensional torus, taking values in Z, given by so the signature is the signature of the Hermitian matrix. The nullity is the nullity of the matrix, and since I did not assume that the C complex was connected, actually here one should add plus the number of connected components of S minus 1. Example, you take mu equal to 1. What do you have? You have that H omega is equal to, so we are summing over two signs. Here we have 1 minus omega bar times A plus 1 minus omega times A transposed. And if you know about the Levin-Tristram signature, this is exactly the way it's defined. So we get back the so-called Levin-Tristram signature and nullity. Okay, and maybe just in the case of the Whitehead link here, since I had only minus ones, we can compute. So you have some, okay, for the Whitehead link, what we get. So maybe I'm just going to compute it at minus 1, minus 1. Here you get the signature equal minus 1, and the nullity is equal to 0. So, of course, the main result that I'm going to state in this talk is actually the following one, which is kind of old now, theorem, which we obtained with Vincent Florent quite some time ago, is that these are actually invariants. So that is, they do not depend on the choice of the C complex you start with. For all omegas. It really has functions. Then you have some further results that I don't want to speak about today, is that actually these are concordance invariants. And then it's for at roots of unity, or at some roots of unity. Yeah. Yes, so really, again, as a subset in S3. Yeah. So if you know anything about the Levin-Tristram signature, you think about it and you think, what could be a nice generalization for links? Then it's this object that will make it, basically. Okay, but what is really nice is, so I think what I will explain now in the last 10 minutes is the first example. I think, I know of cases where the case of one variable is empty, but the multivariable case gives something new. So it's this thing of splitting numbers. So now it's the third part. Talk, results, and examples. So here's the theorem. For any link L, for any omega, we have that the splitting number of L is greater or equal to the signature of the link minus the sum of the individual signatures of the components plus mu minus 1 plus, so I'm going to write it this way, minus eta L of omega plus the sum of the nullities. Thank you. So that's a completely general lower bound. It's very easy to compute again, so maybe I'm going to make an example here for L, the Whitehead link. What do we get? We get the splitting number of L. I'm sorry? I equal 1 to mu. That's eta L. Sorry, eta Li. Thank you, thank you. Thank you.
So that's just what is that? Just
so that's right. That's right. So these things here, they're the Leibniz-Tristam signature nullities. Sorry for the typos. I hope now it's okay. So maybe we just try it for the Whitehead link. So this is greater or equal to. So I said this at my and then we'll take omega equal minus 1 minus 1. What do we get? Here we get minus 1 minus, so the components are 0, so we get 0, plus mu minus 1, we get 1. All these, they are 0, so we get 2. So we get that the splitting number of the Whitehead link is equal to 2. This is by no means an amazing result, but at least it works here. Okay. So again, this lower bound works for any oriented link. It's very easy to compute. And frankly, I mean, I'm going to give you, okay, I have to think how to, I think I can give you the full proof in less than 5 minutes. So, and then I want to show you, so to get the proof, so when we first obtained this result with this elementary proof, we thought, okay, that's all nice, but probably it's totally inefficient. And there's a great surprise about that. Actually, it's not. It's very efficient also. So maybe it's just because the subject is quite young and not enough people have thought about it. But at this stage, it's very efficient. So what I will do, I will try to give you the proof, but kind of hand waving, and hopefully it's gonna work. Maybe the first remark that I should have made earlier when I was talking about signatures is that if you look at the signature of the disjoint union of two links, this is equal to the sum of the signatures. And if you look at the same thing for nullities, it's basically the same, but you get a +1. This is all completely clear because you just take the disjoint union of the C complexes for the two sublinks, okay? Just take disjoint union, okay? So here's the proof, the theorem. Okay, so let's just assume that we have two components, two different components, Li, Lj, and we're performing this crossing change. Let's say Li prime, Lj prime. So what I will do is I will draw locally, I will draw a local C complex for this. So here, Maybe I'm going to take different colors here. It's useful. So let's say this is Sj, and this is Si. And now, how can I obtain, so this is S, how can I obtain a C complex S prime for this link here from this C complex here? Well, it's very easy. You do the following thing. So here I don't change anything. And I simply add a clasp intersection like this. Right? And now here is my new C complex S prime for L prime. Right? And so let's just assume that S was connected. You can always do this. So what do we have? It's extremely easy. We just added the clasp intersection, which means we just have one more cycle coming in. And so we have H1 of S prime is H1 of S plus the class of a new cycle that you don't really care about what he's doing. And then you can compute, so the, let's say, H S prime of omega will be of the form Hs of omega, then some vector, some scalar, like that. And then it's basic linear algebra to show that then this means that, I'll write this here, if you look at the difference of the signatures plus the difference of the nullities, this is equal to 1. Basically, you add one eigenvalue, which can be 0, in which case you have a 1 here. It can be plus minus 1, you have 1 here. So this is equal. But now we're done, because we just... Now let's assume that we have a splitting sequence for L that is of minimal length. Of length equal to the splitting of the link. So now, assume we have L, which is L0, and then you go to L1, etc., and you end up with Ls, which is the disjoint union of the components, the split union of the components, with S equal to the splitting number. Okay? Then what do? You have that the splitting number of L is equal to S. It's the sum I from 1 to S of 1. And this 1, you write it like this. So sigma L I minus 1, I'm not going to write the variables, minus sigma Li plus eta Li minus 1 minus eta Li. And then you use the triangle inequality, and you end up only with L minus Ls plus eta L minus eta Ls. And now it just remains to replace this by the sum of the signatures of the components, and this by the sum of the nullities of the components plus mu minus 1, because you have this additivity thing, and you have the result. I give you the full proof. Okay. So now I just want to use 3 more minutes to tell you that amazingly this is quite powerful. Again, it's not strictly better than anything that was previously known, but it's quite nice. So what do we get with this? So maybe I'm not going to write too much. So first, we have, so we tested this. First, we have 125 out of 130 links with up to 9 crossings, whose splitting number is determined by this, only evaluating at -1, -1. Okay. Then if you use the full thing, we have 2 more, so we have 127. Then if you use the linking bound, this was just for this bound. Now you use the linking bound on top of that, you have 129. So there's a single one up to 9 crossings that we're not able to compute, just using these completely trivial things. Okay, that's the first thing. But this already tells you that it's not strictly better than the linking bound, because there were 2 that we had, and it's not strictly better than the Alexander obstruction, because this is how the Alexander obstruction, this is how the last one is computed. Then second thing, we computed 16 out of the 17 Batson seed links. And there are some examples where the computations of Schaff, Friedel, and Powell took really a full section of the paper, and for us it's 1 line, single line. It's totally obvious. Okay. But there is one that we're not able to get, and they get it by the S invariant, actually. But this one, so Batson seed links, so of the links of Batson and seed. So we're not strictly better than covering link calculus, because this is the way they got. So they use covering calculus and then the S invariant to compute the last one, and we're not able to get it, but okay, it's fair enough. And then I want to show you how it goes with these families of 2-bridge links. So now you consider A1, AN positive integers, B1, Bn minus 1 positive integers as well. And I want to consider 2A1, B1, 2A2, B2, 2AN. So the 2-bridge link with Conway normal form like this. So it's a generalization of the one we had before, right? So I'm just going to draw again the one we had before. Okay. Now, do you see, I tell you there is an obvious C complex for this one. Completely obvious. You just take, so down there, you just consider a disk. Here that you twist, and same thing around here. Okay, anyway. I don't know if you see it. So you have 2 disks. This one is not twisted, this one is twisted. And I tell you that this trick, this is again for C414, but this trick works for this family of links. Okay. You have one disk on top, and you have another disk that you twist and you attach with clasps like that. And so you have this obvious C complex, and now so here, if you think about the splitting number, so this is L, the splitting number of L is less or equal to A1 plus, etc., plus AN, which I want to denote by S. Again, you just think about it, you have to remove A1 of them here, A2, etc. That's the obvious way to split this link. And now you have this C complex, you can just compute the signatures. And I'm not going to do it, but it's really one line again. So if you compute, so for omega equal -1, -1, we get that the signature is equal to 1 minus S, that the nullity is equal to 0, and therefore, if you look at the splitting number of L, it's greater or equal to, so I have 1 minus S, minus the signature of the component which is 0, plus mu minus 1 that is 1, so I get S. So we have the theorem that the splitting number of this link is equal to A1 plus an, which of course is a huge generalization of the examples that were obtained before. Again, so I didn't give you the full proof here, but I think it would be like 2 more minutes to give you this, but since I'm already over time, I'm going to stop here. Thank you very much.